Alright, in this video we're going to go over section 1.4 in the textbook, which talks about complex numbers. So the complex number system is kind of interesting. It's an extension of our real number system. So let's talk about how do we get there. Well, the most basic form of mathematics is counting, and so the most basic set of numbers is the set of counting numbers. So let me draw that right here. Mathematicians represent the counting numbers with this double-barred N because they call it the natural numbers. Almost all cultures in the world have words for numbers. And it's actually, I find it really interesting the way that different cultures have different words for numbers and how it's set up. And you can have number systems that are in different bases. You know, our number system is in base 10, but the Mayans used a base 20 system. The Mesopotamians used a base 60 system. And you can still see some remnants of this in the French language. For instance, their word for 70 is 60 and 10. And their word for 80 is 4 20s, and their word for 90 is 4 20s and 10. So their language builds out of these ideas of 20 and 60. But in any event, I find that to be very interesting. The natural numbers are the most basic set of numbers. But, and this is really an interesting thing, the problem with this is that you can generate an equation using only natural numbers whose solution is not in the natural numbers. So, what am I talking about? If you say x plus 7 equals 2, well, what's the value of x? Well, if we solved this very simple equation, we would find that x equals -5. But notice that -5 is not a natural number. So just this very simple equation leads to the need for an extension of the natural numbers. So, the integers are the positive and negative whole numbers. We use a double-barred z, or mathematicians use a double-barred z to represent the integers because the German word for numbers is Zahlen. Okay? All right. This problem keeps on happening. That's how we get the complex numbers. We'll get there eventually. So what if we wrote another equation using only integers and natural numbers, something like 3x equals 2? Well, again, we can solve this equation and get an answer of 2/3, but notice that 2/3 is not an integer and it's not a counting number. And so that leads to the next extension of the number system, which is the rational numbers, and we use a q because it's a quotient. And so we call this a over b, where both a and b are integers. Okay? And then we keep on doing this. Let's see, what's the next one we want to do? Oh, right, what if x squared equals 2? That's not a rational number, okay? And this is actually something that the Greeks ran into in using the Pythagorean theorem. If you take a square with sides of 1, you find that the hypotenuse is the square root of 2. And the Greeks conception of mathematics stopped here. They thought that all numbers were ratios of whole numbers. And this was a problem that they found very concerning. So this leads to another extension to what are called the real numbers. And I think the best way to represent the real numbers is with the real number line. Even at the highest levels of mathematics, this is where people go to look at real numbers. Every point on the number line represents a real number. Every real number has a point on the number line. And let's see here. If this is 1 and this is 2, square root of 2 is going to live right about there. It's approximately 1.4, but it lives right there between 1 and 2 on the number line. Okay, so what are the complex numbers? Well, the complex numbers come from this problem right here. X squared equals -1. Well, what's the problem here? The problem is that if we take a positive number and square it, we get a positive number. If we take a negative number and square it, we also get a positive number. So what kind of number can we square and get a negative answer? and that's where the complex numbers come in. This is a C with a bar, is the way the mathematicians represent the complex numbers. And the idea is that what mathematicians did is they took this idea of x equaling the square root of -1 and said, well, geez, I don't really know what number that is. You know, the square root of 2, we figured it out. It's somewhere between 1 and 2 here on the number line. The square root of -1, I don't know where that's going to go because anything that's on this number line, when you square it, you get a positive number. This thing, what we're saying is that when we square it, we get a negative answer. And so what mathematicians did is they defined this as being I. The square root of -1, they just said, we're going to call this I, and then any other complex number is going to be a combination of this along with real numbers. And so the complex numbers are defined as a plus bi, where a and b are both real numbers. Okay? All right. So this is all just kind of introduction. This is not stuff that is going to be in the exercises or that I'm going to test you on or anything like that. This is just sort of an introduction to where do these numbers come from. So let's see here. So now, in the same way that the real numbers live on the real number line, the complex numbers live on a complex plane. Now the real number line is here, okay? This is where all the real numbers that we're familiar with exist on this real number line. The vertical axis of a complex number is multiples of I. Okay? And so like I was saying, all the complex numbers are generally expressed as a plus bi. So something like, 3 plus 2i would be right there. Okay? And that's one of the fundamental qualities of a complex number is that it's two-dimensional. Okay? It has both what's called a real part and a complex part. All right? Let's see. Over here, this would be -2 plus I would be right there. Let's say 2 minus 3i would be right there. Okay? So on the exercises for this section are on pages 40 to 42. And on page 40, you've got questions about graphing complex numbers. So here's I'll just keep this little graph right here and look at a couple of these problems here. So in problem 2, we want to find where is 4 minus 3i. So here's 4, here's minus 3i, there's 4 minus 3i. Let's see, problem 4 is -3 minus 5i. Here's -3, we'll put minus 5i on there. So -3 minus 5i would be about there. Let's see, what else? 6 is just plain old -2i. So that means that the real part here is 0, and we just go down here to -2i. All right, problem 8, -1 plus I. Here's -1, there's plus I, so -1 plus I lives there. Okay, I think that's plenty for this one. Like I always say, if you have any questions, just let me know. Okay, it's relatively straightforward. Complex numbers are two-dimensional. It's pretty interesting. I just want to say this before we move on. Mathematicians ran into complex numbers in the 1500s when Italian mathematicians were working on these formulas to solve equations. They kept running into these square roots of negatives and weren't sure what to do with them. And so they just got into this idea where they would just carry it around with them, and if they could add and subtract them or multiply them and combine them, they sometimes came out with answers that were useful. And then they just kind of hung around in mathematics for a while, a couple hundred years, until the 1800s when scientists began to work with electricity. And what they found is that electrical circuits have a couple of measurements that you can use to describe them, and it works really well to plug those measurements into the two pieces of a complex number. And so there actually are applications of these numbers that are very important. Okay, so let's move on and look at the rest of the exercises in this section. And we can calculate with complex numbers in a similar way that we calculate with real numbers. It's not exactly the same, but it is very similar. All right, so let's see here. Over on page 41. So on page 41, this is just about expressing complex numbers as multiples of I. So in problem 14, let's see, it says express each quantity in terms of I. If it's irrational, round it to 3 decimal places. So problem 14 is the square root of negative 81, and that's just going to be 9i, because this is square root 81 times square root negative 1. Square root 81 is 9, square root of negative 1 is I. So there we go. Problem 16, square root negative 49, that's going to be 7i. Problem 18, square root negative 25 should be 5i. Now problem 20, we get the square root of negative 6. Now 6 is not a perfect square, so we're going to have to approximate this. So if we take our calculator, and if we square root 6, right, because this is square root 6 times square root negative 1. So the square root of 6 is 2.449, and square root of negative 1 is I. Okay. Let's see here. Problem 22, square root negative 31. So we can just find the square root of 31. That's 5.568. And then square root negative 1 is I. Oh, and this is approximately equal to. And then there's one more of these. Problem 24. Square root negative 3. And let's see, I think that's 1.732. Yep, 1.732 times I. Okay, and we're going to be doing this when we solve quadratic equations that have complex valued answers. I'll talk more about that in the next video. That's in the next section in the textbook. Okay, so this is just expressing square roots of negatives using I. Because that's the standard way that people express complex numbers, is as multiples of I or in A plus BI form. All right, now calculating with complex numbers. Let's see, if we look at problem 26, we've got 4 minus 5i plus 3 plus 9i. So there's nothing to distribute here. Really, we can just take the parentheses off, and then combine our like terms. 4 plus 3 is 7, positive 9i, negative 5i makes positive 4i, so this is 7 plus 4i. Problem 28, this is a subtraction of complex numbers, so this is 2 plus I, and then subtract 6 minus 4i. Now, here we can just take the parentheses off, but here we have to distribute that subtraction, or negative 1. This will be minus 6 and positive 4i. So 2 minus 6 is negative 4, 1i and 4i make 5i. Let's see here. Problem 30 is also a subtraction problem. This is 8 plus I minus 4 plus 3i. And so, again here, this is still just 8 plus I. This gets distributed, minus 4, minus 3I. So that'll be 8 minus 4 is 4. And then 1I minus 3I is negative 2I. Okay, so there's the adding and subtracting. Now let's look at some multiplying. Problem 32, we've got 4I times negative 8I. This will be negative 32I squared. Now this is where it gets interesting, because a lot of this is just like doing algebra, where you're combining like terms and distributing and doing all these things that we do with algebra. The trick here is that if I is the square root of negative 1, if we square both sides here, this will be I squared. The square root of negative 1 squared is negative 1. So this is equal to negative 32 times negative 1, which is positive 32. And that's our answer for this problem. Okay? This is a really fundamental idea, so it's important that you understand it. Let's say we said something like square root of 16 equals 4. Okay? That's because if we do 4 squared, we get 16. That's the definition of a square root. So that's where this idea is coming from, that I squared is equal to negative 1, because we've defined I to be the square root of negative 1. So when we square it, we have to get negative 1. All right. Now that we know that, let's look at some more tricky problems here. Let's look at problem 36. This is 1 plus 5I times 4 plus 3I. So, like I was saying a minute ago, this works very much the way that algebra does. Okay, when we're distributing and combining like terms, this will be 1 times 4 is 4, 1 times 3I is 3I, 5I times 4 is 20I, 5I times 3I is 15I squared. Okay, now if this were an algebra problem, we would just combine those like terms and then leave it alone. But this is not strictly an algebra problem, because I is not a variable, it's a number. Okay, so over here, the I we just leave alone. All right, but over here we've got plus 15. That I squared is negative 1. So this is 4 plus 23I minus 15, which is negative 11 plus 23I. And that's the result of this multiplication right here. Okay? We'll look at a couple more examples like this. Okay, problem 38. We've got 8 minus 3I times 2 plus I. So, again, we want to distribute here. 8 times 2 is 16. 8 times I is 8I. Negative 3I times 2 is negative 6I. Negative 3I times I is negative 3I squared. Okay, so here we're going to combine like terms in the middle. So that'll be a positive 2I. Over here we're going to replace that I squared with negative 1. So now this is 16 plus 2I plus 3, or 19 plus 2I. Okay, let's look at a few more of these. Let's see here. Number 42, we've got negative 5 plus I squared. So that means negative 5 plus I times negative 5 plus I. So So let's see, negative 5 times negative 5 is positive 25. Negative 5 times I is minus 5I. Then we get another minus 5I, and then a plus I squared. Okay, so this will be 25 minus 10I, but over here, that I squared is negative 1, and so our answer here is 24 minus 10I. Okay. Let's see here. Problem 44, we get into kind of an interesting concept here. 2 plus 6i times 2 minus 6i. So this will be 4 minus 12i plus 12i minus 36i squared. Well, let's see here. These cancel out. They cancel each other out and make 0. Then we have 4 minus 36, and then that I squared is negative 1. So this is 4 plus 36, and so it turns out that actually 2 plus 6i times 2 minus 6i is equal to 40. And this is an interesting idea in that real numbers don't just have real factor pairs, they also have complex factor pairs as well. And we're not going to talk too much about that, but in higher level math courses, people do sometimes get involved in those issues. Yeah, so let's look at one more of these. Problem 46. We've got 5 plus 2i and 5 minus 2i. So this will be 25 minus 10i plus 10i, and then minus 4i squared. So again, these two in the middle cancel out. This is 25 minus 4 times negative 1, or 25 plus 4, which is 29. Now, I happen to find this really interesting. 29 is a prime number in the real number system. It doesn't have any factor pairs. It's only 1 times 29. But in the complex number system, it is factorable into 5 plus 2i times 5 minus 2i. 13 works the same way. 13 is a prime number in the real number system because it's only 1 times 13. But in the complex number system, let's see, you can factor this as 3 plus 2i times 3 minus 2i. Right? Those cancel out. 9 minus 4 times negative 1. 9 plus 4 is 13. That's just kind of a side thing that I think is really cool, but you don't have to worry about it. There's no questions on that in this section. We're just talking about multiplying these together to get that answer. Okay, so one more concept to talk about in this section, and that is the powers of I. So we define I to be the square root of negative 1. Because of that, I squared is equal to negative 1. And we talked about that a few minutes ago. So what if we did I cubed? I to the third power is equal to I times I squared. That makes I to the third, right? Well, we just said I squared is equal to negative 1. So this is I times negative 1, which is negative I. Okay. What about I to the fourth power? I to the fourth power is I squared times I squared. Well, that's negative 1 times negative 1, which is positive 1. That means I to the fourth power is equal to positive 1. And that also means that any other power of I is going to be equal to one of these four quantities, right? Because I to the fifth power is now I times I to the fourth, which is I times 1, which is I. I to the sixth power is I squared times I to the fourth. I squared is negative 1. I to the fourth is positive 1, and so this is just negative 1 again. Okay, so this pattern repeats itself. I, negative 1, negative I, positive 1. I, negative 1, negative I, positive 1. If you think back to that argon diagram that we were talking about at the beginning of this section, these are all the powers of I are right here. Here's I to the first, I to the second, I to the third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, and so on. It just keeps going in a circle like that. Okay? So, to do the last set of problems in this section, what I'm asking you to do is to take these powers of I and simplify them. And the key here is this idea that I to the fourth power is equal to 1. So, there's a couple different ways you can go about doing this. Problem 48, this power is pretty small, I to the seventh power. If you want, you can split off an I to the fourth. Right? And so it's just I to the third times 1, and we know I to the third is negative I, and so I to the seventh is also equal to negative I. Okay, let's see here. Now another way to go about doing this is to take this power and divide it by 4 and see what the remainder is. Now, when I do this division like this. 7 divided by 4 goes in 1 time with a remainder of 3. And notice it's equivalent to I to the third power. Okay? And what this is doing is that's pulling out all of these I to the fourths because every I to the fourth is equal to 1. And then all you're interested in is what's left over besides these 1s. Okay? Now, if you do this on a calculator, like I know a lot of people do, you do 7 divided by 4, and it's going to tell you 1.75. So, if you see the 0.75, that means I to the third power. If you see a 0.50, which is remainder 2, that means it's I squared, which is negative 1. If you see the 0.25, which is remainder 1, that means it's I to the first power. And if you don't get any decimal to your answer, if the 4 divides evenly, that means you're just talking about 1. Okay? For instance, I to the 8th power is I to the 4th squared, which is just plain old 1. And if you did the 8 divided by 4, you would get a 2 with no decimal piece. Okay? All right, let's look at a couple more of these problems. Let's see here. Problem 52 is I to the 56th power. All right, so let's see. I guess I'll do this on the calculator since I know that's what most people are going to be doing. So if you do 56 divided by 4, we get 14. Exactly. Which means that this is equivalent to 1. Okay? Because I to the 56th power is I to the 4th raised to the 14th power, which is just plain old 1. All right. Let's see. What else here? Problem 54. I to the 35th power. So, if we do 35 divided by 4, that should be 8.75, which means this should be equal to negative I. Okay? If you want to break this down, this is going to be I to the 4th to the 8th power times I cubed. There's your I to the 32nd, I to the 3rd, that makes I to the 35th. And so that'll just be negative I. Okay, let's see here. Oh, what else do we want? Yeah, let's do problem 62. I to the 9th power. If you do 9 divided by 4, that'll go in twice with a 0.25 left over. That means this is just equivalent to I, because this is I to the fourth times I to the fourth times I. And that's 1 times I, so that's why it's equal to I. Okay, so for this assignment, I'd like you to work your way through these problems from 1 up to 61, just the odd ones. And then I'll have a quiz with a bunch of these questions on there. And then in the next video, we'll talk about section 1.5, and that involves solving quadratic equations that have complex numbers as answers.